Okay, let's go ahead and work this Bernoulli's equation example. In this example, we have this tank, a 5-meter tall tank of water, and we're told that there's a piston on the top, and the piston pushes down on the water, and it forces water essentially out of the bottom of this this tank. And we want to know, what is that velocity? Okay. Now, so here's Bernoulli's equation. So we have to figure out all these various parameters that go into Bernoulli's equation. So we need to know pressure, volume, y height of several points in the fluid. Now, since we're interested in the velocity over here, we'll consider this over here our point number 2 to apply Bernoulli's equation. Okay? The point right where the fluid exits the tank, because that's where we're interested in the velocity. And the other point in this fluid that we'll consider will be right at the top, right there. Okay, that's our first point, literally right on the top of that body of water. So let's go through here and identify our various parameters for points 1 and point 2. Now P1. Okay, we're told that this piston applies a pressure of 1.3 times 10 to the 6 pascals. Okay, so they're 1.3 times 10 to the 6. However, we're told that's the gauge pressure. And remember, the gauge pressure is the amount above or below atmospheric. And so in Bernoulli's equation, the pressure is the absolute pressure. So therefore, to get the absolute pressure, we have to actually add atmospheric to this. Okay. Now, V1, what's the velocity at point 1? Well, the velocity at point 1 is 0. Okay, the fluid is stationary right there. Now, Y1 comes into Bernoulli's equation as well. Y1, we'll take this, it's a 5-meter tall tank, so we'll take the height of the tank. Y1 is 5 meters. So that's 5 meters. Okay, now we need to do the same thing for point 2. Okay, so the pressure at point 2 here, well, that fluid is exposed to the atmosphere. So therefore, the pressure at point 2 is atmospheric pressure. Okay, anytime that fluid is directly exposed to the atmosphere, it's going to be at atmospheric pressure. The velocity at point 2, well, that's what we're interested in. That's the question. And the y height of point 2, we're taking that height as 0. Okay, so we've gone through and we've identified the various values that we plug into Bernoulli's equation. So let's plug these all into Bernoulli's equation now. P1 is 1.3 times 10 to the 6 plus atmospheric pressure. Okay, 1/2 V1 squared, V1 is 0, so that term is 0, plus rho GY1. So the density of water, remember, is 1,000. And, you know, I'm going to drop the units here because I'm positive we have them all in the right units. This is in pascals, that's the right unit. The density of water is 1,000 kilograms per cubic meter. G is 9.8. Plus the y height, which is 5 meters. Okay, so that equals P2, which is atmospheric pressure, plus 1/2 density of water, which is 1,000. Kind of running out of space over there, times V2 squared. Okay. Then finally, our last term, rho GY2, Y2 is 0, so that term is 0. So here's our Bernoulli's equation then. We've plugged that stuff in here. Now, atmospheric pressure appears on both sides of the equation, so that cancels out. Okay, so now all of this is an arithmetic problem now. Take this, add it to 1,000 times 9.8 times 5. Then to find V2, you have to multiply everything over here by 2, because that 1/2. and then divide it all by 1,000. That gives you V2 squared. So then you take the square root of all that, and you get that velocity at point 2. The number I got here was 51.9 meters per second. Pretty fast. You know, that's over 100 miles an hour. So that's going to be a pretty powerful flow there. And that's mainly due to the action of this piston, which is really pushing down on that fluid with a lot of force. Now in part B, we are asked, how fast would the fluid be exiting if that piston weren't here? Okay? So in other words, that would be the same situation in all above here, except that now the pressure at point 1 would just be atmospheric. Okay? You take that piston away, and point 1 is now exposed to the atmosphere. So the pressure at point 1 would just be atmospheric pressure. So this term would go away. Everything else is the same. So when you come down here and do the math, this term goes away. Okay? And all you'd be left with then is this part right here, which is basically density times G times Y1 equals 1/2 rho V2 squared. And that gets back to the situation that we talked about in lecture, where the velocity then that it exits would basically be given by the free fall height. Okay? And so when you do this calculation, 1,000 times 9.8 times 5, then times 2, then divide by the density. Well, really, the densities would cancel out again. They're equal. Okay? And what you would get when you do that calculation, you get a much lower velocity. You get V2 is 9.9 meters per second, so considerably lower. And that 9.9 meter per second value is about 20 miles per hour, a little over 20 miles per hour. That's the free fall velocity. If you just take something and drop it from 5 meters, well, after falling 5 meters, it's going to be traveling at 9.9 meters per second. And that's the same speed with which the fluid would leave this tank if there were no piston present there.